Welcome to 11th problem solving session of the course, Spectroscopic Techniques for Pharmaceutical and Biopharmaceutical Industries. Today we'll be dealing with a couple of problems which is pertinent to NMR spectroscopy. So without further delay, let's go to the first set of problems. So NMR not all the atoms. I hope I'm audible. If I'm not audible, can you please comment? Can you please post a message in the chat box? Yeah. So NMR active nuclear magnetic resonance has been shown by nuclei which have non-zero spin angular momentum quantum number, and so it can be differentiated based on the mass number and the atomic number of the nuclei or the atom that is that you're interested in. So we have been in the first problem we have been asked a couple of isotopes of boron and carbon, and we have been asked to find which is NMR active. So in case of as you may know, in case of boron, the atomic number is in case of boron, the atomic number is 5. In case of carbon, the atomic number is 6, right? And we have to find which isotopes of boron and carbon are NMR active. So in the class, we have been told that whichever nuclei which has its atomic number is odd, all its isotopes are going to, irrespective of whether the mass number is odd or even, it is going to be NMR active nuclei, right? So in case if we have a even atomic number atom, in that case, if the mass number is odd, then the nuclei is NMR active. So in case of boron isotopes, all these isotopes are NMR active because its atomic number is 5, and so nuclei with the odd atomic number is NMR active. So that's why all isotopes of boron are NMR active. Based on their natural abundance, we'll see the NMR signals of these isotopes. In case of 13C, C12, 13C and C12 isotopes of carbon, so the atomic number of carbon is and it is odd. It is even. So when you have nuclei with even atomic number, if the mass number is odd, then it is NMR active. If mass number is even, so or nuclei with even atomic number and mass number, is NMR inactive. So the set of nuclei which are definitely NMR active is nuclei with odd atomic number, and the nuclei with even atomic number and even mass number will be NMR inactive. So in that case, C12 is NMR inactive because it falls into the category of both even atomic number and mass number. But C13 has a even or odd mass number, so odd mass number, hence it is NMR active. Second part here is sort of more than a question. It is to make you understand how the energy level diagram of a spin half system and a spin 1 system will look like. So yeah, the term spin half or spin 1 comes based on the one second. Okay. So the spin half and spin 1, the terminology come from the spin angular momentum quantum number or the angular momentum quantum number, and sorry, yeah. So it is being denoted as I. I is equal to 0 for NMR inactive nuclei, and I is equal to 1 by 2 for spin half system, spin half nuclei for spin half system. When I is greater than half, those are called quadrupolar nuclei. Okay, so we have been asked to show how the energy diagram of spin half system look like. I think it has been covered in the class. For just for a one more round of clarification, I'm just so in case of a spin half nuclei, the spin can adopt two orientations where m is equal to plus 1 by 2 and m is equal to minus 1 by 2. Okay, now let's talk what is m. So m is the magnetic quantum number, and it can adopt values from minus I to plus I, or like minus I plus 1, things like that. So in this particular case, this is how the energy level diagram of a spin half nuclei look like, and the energy corresponding to the state will depend upon sorry where um, M is these equation has been covered in the class. I'm just giving you a brief I'm just briefing it over again. So yeah, energy of and for plus half it is going to be, so it is M is equal to plus half E plus half is equal to minus 1 by 2 gamma h cut B naught. E minus half is equal to plus 1 by 2 gamma h cut B naught. You can just substitute m in this particular equation and get this one. And the energy gap between these two is E minus half minus E plus half. So that is 1 by 2 gamma h cut B naught. Minus of minus 1 by 2 is going to be plus 1 by 2 gamma h cut B naught, which make it as gamma h cut B naught. Okay, so the energy gap between these two, delta E is equal to gamma h cut B naught. Now let's see how it is going to look it in the spin 1 system. I think I may not have one more slide. So for spin 1 system, I is equal to 1. M can have values minus 1, minus 1, minus 1 plus 1 is 0, then till plus 1. So different M values, magnetic quantum number that the spin 1 nuclei can adopt is minus 1, 0, 1. M is equal to 0. So these are the different M values. And the E is going to be minus M gamma h cut B naught. So for M is equal to 1, E is equal to minus gamma h cut B naught. For M is equal to 0, it is going to be 0. For M is equal to minus 1, it is going to be gamma h cut B naught. Okay, so this is how the energy diagram will look like. And we had seen in the class that the the atom can jump from a state where M is equal to minus 1 by 2 to plus 1 by 2, and it has been supported by the selection rule delta, where delta M is equal to plus or minus 1. So the only allowed transitions is when the delta M is plus or minus 1. So in case of a spin 1 system, we can go from M is equal to 1 to M is equal to 0, and we can go from M is equal to 0 to M is equal to minus 1, but M is equal to 1 to M is equal to minus 1 is not allowed. Okay, So yeah, this is how the energy level diagram of spin 1 nuclei look like. So we can make similar diagrams for spin when I is equal to 3 by 2 or I is equal to 5 by 2, things like that. And it will become more complicated. In general, we deal with spin half systems where we have the angular momentum quantum number to be 1 by 2. So in general, we follow such nuclei. Yeah. So next, so in this energy equation, you had seen there is a value called gamma. I haven't explained all the terms in this energy equation. So yeah, it has minus m gamma h cut b naught, where m is the magnetic quantum number, gamma is the gyromagnetic ratio. H cut is the Planck's constant h by 2 pi. B naught is the bulk magnetic field. B naught is the external bulk magnetic field into which we'll keep the nuclear spins which let it to align to one orientation. So the two orientations that is allowed for a spin half nuclei is plus 1 by 2 or minus 1 by 2. So this is for one particular spin. So what happens when you have an ensemble of spins, or like when you have a set of spins? Consider you have a 1 molar sample. So in that case, you have around 6.022 into 10 to the power 23 molecules or atoms, depending upon what is your sample is. So what happens to those 10 raised to 23 molecules? So we'll have most of the spins aligning in this particular orientation with the m value of 1 by 2, and you have some spins which is aligning like this with the m value of minus 1 by 2. This happens when you place the system inside the magnetic field. So you have this happens when you have a P0 field in this particular direction. So this is what happens when you put a system with here I am just representing with a couple of spins, right? So if you have some 10 raised to 23 molecules, most of them will align. Almost a little more than half will align along m in the orientation of m is equal to 1 by 2. A little less than the half of the molecule. So this is 10 raised to 23. So maybe 10 raised to 11 molecules will orient along m raised. Sorry. 10 raised to 11 molecules will orient in this direction, whereas the molecules 10 raised to 12 molecules will orient in the other direction. It's not exactly, I'm not giving you the correct values. Yeah, we can calculate it, and I think sir has calculated the number of molecules which will orient in these with different m values in the class. So what I'm saying is this will be the number of molecules which will orient, or number of nucleides orient in with plus m by 2 orientation will be always higher than the molecules in the m is equal to minus 1 by 2, which is like n plus 1 by 2, number of molecules in plus 1 by 2 is greater than n minus 1 by 2. So this in turn generates a plus Z magnetization. So you have more of the molecules over this direction, it generates a Z magnetization along this direction. A little extra number of molecules here orienting in this direction will generate a plus Z magnetization. This is what we are going to flip or detect eventually in an NMR experiment. I don't know how much I made sense. So I just want to give you an intuition that the spins will have the, I mean, individual spins, the individual molecules or atoms that you're giving in the sample will give you, I mean, um, will orient in different directions. And what gives the bulk magnetization, which you will play with, or which eventually you will detect in the experiment, is going to be the plus Z magnetization. It is because of the orientation of all the spins present in the system. Okay, so let me go over a little bit more about the gyromagnetic ratio. So gyromagnetic ratio is a property of it's the property of a particular nuclide. And yeah, here we have been given a set of commonly used NMR nuclides, and we have been asked to differentiate it based on its sensitivity. So okay, uh, let's look at the so sensitivity is sort of directly proportional to the energy gap between the states, and we know delta E is equal to m gamma h cut p naught, or sorry, not m gamma. There is some problem. Yeah, sorry. One second. There is some problem with the system that I'm using. Okay, it's fine. So gyromagnetic ratio is the property of the nucleate, and it so the sensitivity depends upon the energy gap between the states, between the ground states and the ground state and excited state, or like yeah, excited state. In this particular case, it is energy gap between E plus half and E minus gap in E minus half. And so we know that delta E is equal to gamma h cut p naught, and it so we know that at a particular magnetic field, if you are keeping it to a particular magnetic field, the only other thing that the energy gap will depends upon is the gyromagnetic ratio. I'm not going to, it's a more physical intuition. I just want to give you a understanding about how different are these gyromagnetic values are. Yeah, so if you how are it for different commonly used nucleus? So for proton it is 27. For proton it is 26.75. For carbon, 13C carbon, it is 6.7. For 15 and nitrogen it is minus 2.7. For fluorine it is 25.18. For 31 phosphorus it is 10.83. All these nuclei here, proton, 13C, 15N, fluorine and 31 phosphorus, all of them are spin half nuclei. Whereas deuterium 2H, which is deuterium, is a spin 1 nuclei and its gyromagnetic ratio is 4.1. And these are multiplied with 10 to the power 7 and the values are in radian second inverse Tesla inverse. Sorry, radian inverse second Tesla inverse. Sorry. Yeah. So so it is a radian seconds Tesla inverse, and it's 2.26.75 into 10 to the power 7 radian second inverse Tesla inverse for proton. Proton, carbon, 15 and 19F and 31 phosphorus, all of them are spin half nuclei, whereas this is spin 1 nuclei. And do you know which nuclei will have a higher? So okay, so based on whenever you have a higher gyromagnetic ratio, that's when you have the higher energy gap, which in turn results in a higher sensitivity of the experiment, higher sensitivity of that particular experiment. So in this particular case, which one would have a higher sensitivity? The one with the higher gyromagnetic ratio, right? So the one with higher gyromagnetic ratio in the set of nucleides is proton, which is 26.75 into 10 to the power 7 radian inverse seconds Tesla inverse as gyromagnetic ratio. What happens to then the next one is going to be fluorine, which is 25.18. So proton greater than 19F, greater than, next one is going to be phosphorus. It has 10.83 into 10 to the power 7 radian inverse second Tesla inverse gyromagnetic ratio. So 31 for phosphorus, and this then comes the 13C carbon, and it is with 6.7. and what happens, the next one is going to be 15, next one is going to be deuterium, and it has a gyromagnetic ratio of 4.1. next is 15N has the least gyromagnetic ratio value. It's not the negative sign that makes 15N at the end. It is the magnitude of the gyromagnetic ratio that made the 15N at the end. So if you would have had to put in 15N or 14N, where 15N is a spin half nuclei, whereas 14N is a spin 1 nuclei. And if we have to see which one is more sensitive, if you look at the gyromagnetic ratio of 15N is going to be minus 2.7, whereas 14N is 1.9. This is the gyromagnetic ratio. This one multiplied to 10 to the power 7 radians inverse second Tesla inverse. And between these two spins, nucleus 15N would have higher sensitivity than 14N. So the sign we are not actually considering. It is just the energy gap, that the magnitude of energy gap is what matters. So yeah, that's why it is irrespective of the 15N is at the end in this particular order, not because it has a negative sign in the gyromagnetic ratio, but because of the lowest magnitude of the gyromagnetic ratio. I hope you understood why. It doesn't matter what is the sign of gyromagnetic ratio. What matters here is the magnitude of gyromagnetic ratio, and according to the chart that we have made now, the one with the highest gyromagnetic ratio, which is proton, is much more sensitive than any other nuclei, be it fluorine, phosphorus, carbon, or nitrogen. So if we correlate how different, how many times it is going to be. So proton has 4 times the sensitivity of 13C, whereas proton will have 10 times, around 10 times sensitivity of 15N. These are just I'm just giving intuition of how sensitive different nuclei are. So if you want to perform the experiments on carbon, you are sort of losing 4 times the sensitivity compared to a proton based experiment. And yeah, fluorine and proton sort of have similar sensitivity. Yeah. Do you know any nuclei which has a higher gyromagnetic ratio than proton, which is 1H hydrogen? So the tritium, which is the other isotope of hydrogen, which is a spin half nuclei. Sorry, which is a spin half nuclei, and it has a gyromagnetic ratio of 28.53 into 10 to the power 7 radian inverse second Tesla inverse, and it is obviously higher than the proton because of the low abundance of the tritium. That's why we are not using it for studying any of the molecules. So the energy gap is because the sensitivity is directly proportional to energy gap between the two states. The energy gap is directly proportional to the gyromagnetic ratio. Depending upon the gyromagnetic ratio, we have the NMR. We have the sensitivity of different. The sensitivity varies based on the gyromagnetic ratio of different nuclei. So that's what this part. That's how this particular problem ends. The next thing is it's about the one pulse experiment. I think this has been covered in the class. I just want to show how the magnetization is going to evolve during this process. So I had previously shown that irrespective of having a m is equal to plus half and m is equal to minus half, if we put it inside a B0 field orienting along orienting in this particular direction, we will generate a plus Z magnetization if you have a set of for a I had shown it in the previous slide, in the first question itself, how we generate the plus Z magnetization with different orientations that the spins can adopt. And yeah, so what happens is this plus z magnetization, the small plus z magnetization that has been generated by a large number of spins is being rotated during an NMR experiment, and this plus z magnetization, whatever is like left, is what we are going to detect. So yeah, I don't know how this will go. So a one pulse experiment um, as shown in the course lectures. We have a 90-degree pulse and we have a acquisition time during which we detect the magnetization, detect this magnetization which is shown in the green color. So yeah, so we have B0 field, I think. And what happens with the pulse? With the pulse, which will be applied along one of the, so both the B0 and the effective magnetization, the magnetization that you see from the large number of spins is along Z axis, and you apply a pulse from X or Y, one of the perpendicular axis. What it does is it put the magnetization along, so it put the magnetization along one of the transverse axis, which is both perpendicular to this direction of application of pulse. And what we sort of detect is going to be this particular magnetization. This is what we are going to detect, and this will be detected based on the coils that is being there. In the transverse axis, we have coils using which we detect the magnitude of the magnetization. Okay, not just the magnitude of magnetization at every time point. So at one time point, another time point, things like that, using by plotting the intensity as a time domain. So the magnetization, okay, m y of so this is, if this is x-axis, this is going to be minus y. So m minus y of, okay, sorry, m minus y of t, we are going to, at different time points, you detect the magnitude. And by this is how your time domain signal is going to be. So you sort of detect how much is the magnitude of this magnetization at different time points in this particular axis, and by plotting it as a function of time, we will get a time domain signal, and you Fourier transform it, and you will get a, sorry, Fourier transform it, you will get something something as a frequency domain spectrum. So Fourier transform is a mathematical operation to transfer. Yeah, Fourier transform is a mathematical operation to transform time domain signal to frequency domain signal. Okay, so this is how in general one pulse experiment look like. So we have already seen how a bulk magnetization is being generated. Nuclear spin can have two different orientation. For a nuclear spin, nucleus with the angular momentum quantum number 1/2 can have two different orientation, which is with a spin with m is equal to plus 1/2 and plus m is equal to minus 1/2. For a large number of spins, the number of and the number of nucleus in 1 by 2 is going to be higher than n is equal to minus 1 by 2. So this in turn generates a magnetization along the z-axis, where to which the which is also the direction of the bulk magnetic field, and you are going to flip that magnetic field to the transverse axis where the detection coils has been kept. So the detection coils are somewhere in the transverse axis. So what you do is you flip this magnetization to the transverse axis to detect it, so that you can get an idea of what are the frequencies at which it processes along the processes around the bulk magnetic field. So what happens is, so you have the magnetic field magnetization flip to the transverse axis where you have kept the where you have kept the coils, and this will process the magnetization in the transverse axis will process with its Larmor frequency. And what we then do is detect the intensity. So what these coils will do is it will detect the magnitude of magnetization along that particular direction at different time points, which will give us a time domain spectrum, and this time domain spectrum will be Fourier transformed to get the frequency domain spectrum, which will sort of give us the so-called which will give us the NMR spectrum that we see. So this is how a normal one pulse experiment works, and the frequency at which it processes around the B0 field is its Larmor frequency. And we'll get in the spectrum we'll get the in the frequency domain spectrum we see a peak, Lorentzian peak, where at the Larmor frequency of the spin that we are interested in. Okay, so this is how a one pulse experiment work. I hope you understood how the magnet how are we having a magnetization when it is kept in B0 field, and how are we pushing the magnetization why are we flipping the magnetization to transverse plane, and what are we detecting, and how do we see this detected spectrum detected signal as a frequency signal, as a frequency spectrum that we in general observe. So yeah, this is a question where we have been shown a couple of molecular compounds, and we have been asked to find which all will in general show an NMR spectrum, which all nucleides will show NMR signal. So it is a CF3 CO CH2 CH3. So this is the first molecule, and yeah, we have to find which all molecules will show the which all nucleides will show the NMR signal. So to show for a nucleate to show NMR signal, I has to be not equal to 0. So we know that for fluorine, F19 has a the I value of 1 by 2, and for carbon 13C, I value is 1 by 2. So fluorine will show here, carbon will show here, and this carbon will also show here. What about this oxygen? Will these oxygens be will they be NMR active? What do you think? Can someone say unmute and tell whether we can see oxygen here? Yeah. So yeah, we cannot see oxygen here because right? So it has a I value of 0. Check. I value is equal to 0. So we can't see oxygen. We can again see this carbon, these two protons, these protons, this carbon. So for this particular compound, we can see for carbon, fluorine, proton, right? We can see for these all these atoms, all these nucleases. We cannot see it for oxygen. So why don't you tell it for this particular system? So it is like a HCON CH3 CH3. In this particular case, which all atoms will, which all nucleides will show NMR signals? Will proton show a signal here? What about carbon? Nitrogen? So the most abundant isotope of nitrogen is N14. So will N14 show a signal? Yeah, okay. Proton will show a signal for sure because we have lot of protons here in this particular system, and all these carbons which will be 13C labeled will be 13C carbon will show signal, and 14N and also 15N, the natural abundance 15N and the 14N, which is the most abundant isotope of nitrogen, will also show signal, but it has an I value of 1. This has an I value of 1/2. Yeah. Then the next one is PCH3 thrice. So it's going to be will phosphorus show a signal? Can someone answer whether phosphorus will give a signal? If so, which isotope of phosphorus can give a signal? Yeah, P31 of phosphorus can give a signal. We had seen it in the previous question. P31 can give a signal. And proton, and obviously 13C carbon and 1H proton can give you signals. So that's sort of come to the end of this particular question. So we have been just asked to find which all nucleides will in this particular compound will show a signal. The next question is about the resolution and sensitivity of different NMR instruments at different B0 fields. So a researcher has purified 500 microgram of an organic compound, which is very unstable. So we have to finish the experiments very quickly. And the NMR facility of that particular institute have 2 NMR instruments, and it is at 2 different B0 fields at 9.4 Tesla and at 9.4 Tesla and 14.1 Tesla. Which instrument would that researcher choose to record a proton NMR spectrum of that particular compound? So he has only some 500 microgram of compound. So the concentration of your sample is going to be very less. So which instrument would that researcher choose to perform the experiment? So one is a 9.4 Tesla, the other one is 14.1. So he has to do it really quicker. So which one will give a higher sensitivity in a smaller time? So how can we do this question? So we had seen in previous slides that sensitivity is directly proportional to energy gap, right? And delta E is gamma H cut B naught. right? And we are going to measure it for proton. So the gyromagnetic ratio is the property of a nuclei, and it is not going to change depending upon the B0 field. So delta, we had seen from this equation, we can say that delta E is directly proportional to B0. So as we go higher and higher in B0 is when you see a better sensitivity for that particular organic compound, right? So when it is, so which instrument would that researcher should choose? Should he choose 9.4 or 14.1? What do you think? Yeah, we have to choose 14.1 um, 14.1 Tesla instrument, because that's when you have the higher energy gap between the ground state and the excited state of your um of the nuclear spin states, and which will in turn increase the sensitivity of the NMR signal that you observe. So yeah, so that's why I hope you sort of understood why I am stressing about the energy gap. So um, so the plus Z magnetization that you when you have a spin half nuclei plus 1 by 2 and minus 1 by 2 orienting in two different direction, and you have n 1 by 2 greater than n minus 1 by 2, and the sensitivity truly depends upon the number of molecules in the number of molecules in the uh, how high is the population difference between the ground state and the excited state. So that is which in turn generates the Z magnetization, right? As long as you have higher and higher molecules in plus 1 by 2, your mz value will increase. So when you your Z magnetization value will increase, the magnitude of Z magnetization will increase. So you would prefer to have higher and higher value in the value of the higher and higher number of molecules in the plus 1 by 2 state. So what we sort of detect is going to be something in whichever is coming to minus 5. This is what we are going to detect, the magnetization whichever was here. So depending upon how much amplitude you had, that much intense will be your sorry that much intense will be your signal to be your signal to be. Okay, so yeah, so that's why performing the NMR experiment at a higher B0 field would be beneficial, because you already have very little amount of molecule, very little amount of the sample, and it's very unstable. It's going to be um, coming out of the sample very soon. It's going to be destroyed very soon. So it's important for us to do it at a very sensitive sensitive instrument rather than a less sensitive instrument. Yeah, this is the last question that we'll be addressing today. Mm, yeah, which we'll be addressing today. It's about the resolution. It's going to be the resolution in that we get in NMR spectrometers. So in a 200 megahertz instrument, okay, we observe a doublet around 2 ppm. This is at 2 ppm, and the coupling constant between this doublet is 10 hertz. So we have been introduced to class what is a coupling constant. So when you have a proton attached to a carbon and it has another carbon, okay, let me just give you an example. So you have ethanol. How does this NMR spectrum will look like? The proton NMR spectrum for this compound will look like. It will have so different protons will show different chemical shifts. Chemical shifts being the signature of different different electronic environment, electronic or chemical environment that a particular nuclei experiences. So if you consider this OH is a sort of experiencing a strong pull of this proton is experiencing a strong pull of electrons from its electron from it to this particular oxygen, because this oxygen is very electronegative. So you see a one signal for OH, which is very much downfield at very much down at very much a downfield part of the spectrum. So you must be aware of what is downfield. Downfield is when you have less electronic cloud around your spin. So here we are detecting this proton. All this electron cloud over this proton is being dragged by oxygen, which is very electronegative. That's why we have the oxygen being downfield, which is at very high delta value, which is the higher chemical shift value. And then you will see something like this proton, which is also comparatively closer to this oxygen compared to this proton here. And these two proton sort of experiences same chemical shift. I'm sorry. These two proton experiences same chemical shift, and that's why it will be double the intensity compared to this one. And I'm just only introducing chemical shift now. We'll come to scalar coupling in a bit. Then the one here, the protons which is at this carbon away from this oxygen, a carbon away from this two carbons away from this oxygen, it will resonate most upfield and it will have highest intensity because it has 3 protons contributing to it. So this is from 3 protons, this is from 2 protons, and it is more upfield. It is more at upfield, which means it has lower delta value. So this will be at 0.2. This will be at this will be at 1, and this OH will be at 4 ppm. So this is how I'm just giving a relative value just to make you understand how the chemical shifts are going to be for different nuclei, different proton in different chemical or electronic environment. So depending upon how far it is from an electronegative nuclei, the chemical shift is going to be different, and depending upon how many protons contributing to that particular signal, the intensity will be different. So in this particular case, in this particular when you look at this particular proton, which is the OH, it is next to it has a neighboring 2 protons, so which makes this particular proton signal to split into 3. So we'll get a triplet. Okay, in case of this proton, okay, so I'm writing it over and over. When you compare these 2 proton, it is next to 1, 2, 3, 4 of them. So it will form 5 lines. You can check how is its intensity going to be. I think sir has covered it in the class. So you can go over how the intensity is going to be. So it also split based on, depending upon the number of neighboring spins. So this will split into 5 peaks, which is a quintet. And when you compare, when you look at this proton, it has 2 neighboring protons, right? 1, 2, and because of which this signal will split to sorry, yeah, this will split to again a triplet. Sorry, in 1:2:1 ratio. Okay, so this is how the chemical shift and scalar coupling um, for a particular for a particular nucleus or for particular spin in a compound. So here in a 200 megahertz NMR spectrometer, a molecule shows two doublets separated by 2 ppm. I don't know whether I have time to finish this off today. If not, we'll address this in next problem solving session. So it has two doublets, and two of these doublets have coupling constant of 10 hertz, and it is separated by 2 ppm. Okay, so what is going to be the separation here? So the separation in this particular case is, in chemical shift it is 2 ppm. How much it is in the hertz? It will be separated by 2 into 200 hertz. Okay, I think this may need a little bit more explanation. Maybe a little bit more explanation about how the chemical shift formula is and things like that. Maybe I'll address this in the next tutorial, next problem solving session. Okay, it's going to be we are going out of time today, so I'll definitely discuss this in the next problem solving session. Yeah, if you have any particular question with these explanations that we had today about NMR active nuclei and how the bulk magnetization is being generated, and how sensitivity is different in different nucleides, and about the one pulse experiment, or how the sensitivity is being correlated with the B0 field. We can have a short discussion now if you have anything like that. Yeah, we are going a little over time, so I understand that. Otherwise, I would have finished this particular problem as well. Do you have any particular question? You can also comment and text your message in the chat box. If you all don't have any particular question from today's problem solving session, let's end the session for today. Thank you very much for all to join.